Can we build autonomous storage systems that can adapt to changing application workloads? Irfan Ahmed, founder at Magnesian, explains how breakthroughs in autonomous storage systems research can deliver impressive gains in cost, performance, and latency control. Over to you, Irfan.
I am Irfan Ahmed, the CEO and founder of Magnesian.io. Magnesian.io is a company focused on providing technology and algorithms for the future of storage and memory hierarchies, in particular for fully automated and fully autonomous storage systems. So the key question to start with is, does the storage industry and memory industry, do we need fully autonomous systems? What's been happening obviously in the last few years is difference and divergence in available technology that uses artificial intelligence, machine learning, and wide-scale data analysis to automate tasks for consumers. And today we have autopilot systems and self-driving and fully autonomous systems that are being prototyped and actually being tested on California roads. We can now look at some of these technical breakthroughs that are enabling in the specific area of performance autonomy. So modeling performance in real time is a new area of some breakthroughs which are enabling low-cost, real-time, efficient, and accurate modeling of storage systems with millions of IOPS has traditionally been not possible in real time. Even offline has been exceedingly expensive, so that even if you weren't able to learn the system well offline, you run the risk of the actual dynamics of the system having changed dramatically by the time that you have learned the behavior of the system, and now your learnings are stale and it's hard to justify implementing those in a loop. So here, this task is really about learning the performance model of the joint model of the workloads, the applications, and the storage system and how they interact with each other. And if we're able to do that, lots of different flavors of models can be built, but fundamentally they're all just functions of the workload, the resources available, and the parameters of the storage system. If we can model storage performance in real time, we gain a lot of these capabilities. So, but what are these performance models? So here I have taken just a single dimension and I have simplified it down to latency, so lower is better, and the cost of the aggregate resources allocated to the storage system to achieve that latency for a given workload. So this right here, the red curve, is a real customer's real production workload. You notice that as we add resources, which is on the x-axis towards the right, if we're adding cost and dollars, that performance does improve. Latency does decrease. But the interesting challenge that has been well known in the storage world is that the improvement in performance, or in this case, lowering of latency, is not a linear function. It has all these step functions in it, all these cliffs. And there are plenty of times where you could 2, 3, 4x the resources that are allocated to a particular application or workload, or a combination of applications and workloads without much increase in the performance. So here in this example, which again is a real customer production use case, if we increase the cost of the system by allocating more of the tier 0, tier 1 storage by 2x, so now having double the budget. Imagine going from $1,000 a day for this workload to $2,000 a day and not seeing any interesting performance improvement. And we might then go and try to take it to 3 or 4x. Maybe we're bold enough, we'll go to 8x. At some point in time, we will give up. I will give up at 8x if I was doing this manually. And if I give up at 8x, now I don't realize, but I'm actually at the cusp of a fairly steep improvement in latency if I was to just continue to increase the resources that I'm giving to the system. Only a fully autonomous system has access to that red curve, and then the ability to make decisions based on this, right? So in this particular case, it was perhaps better to not expend 8x the resources for no performance benefit. So suppose you're currently sitting at where you're at the cusp of performance improvements, right? This point, turns out, for this particular workload, is actually the least efficient point to operate, because had you allocated 1/8 the resources, you would have achieved the same performance. And had you allocated just another 30% of resources, you would have had a precipitous improvement in lowering of latency. In other words, you always want to operate at the bottom of these cliffs, at the talus of these cliffs. And if you're able to do this in a fully autonomous system, you can now have a very useful, powerful trade-off, which allows you to trade off cost and performance dynamically based on the requirements and needs of that workload. So this is a very quick overview of just one dimension of these autonomous performance models that can be constructed, and the ability to be able to construct them is net new. You're hearing about this probably for the first time. That's how fresh this research is, and this involves several peer-reviewed papers that can be referenced and found at Unix ATC, FAST, and Sigmetrics that have created the ability to build these types of models in real time. Now, here are some sample models for production applications. I'm highlighting T09 here. Again, customer workloads. So the names of the customers and their workload identity has been elided here. And in this case, you'll see 120 gigabytes worth of resources allocated to the highest tier before any performance improvement is seen. So again, just imagine going from 10 to about 130 before seeing any performance improvement. That's a 13x increase in the physical resources. And very few of us would have the patience to really search that space manually, because again, that red curve is not available today in our traditional systems. So that red curve is the internal representation of the autonomous performance model that a fully autonomous device has access to. And this is the stuff I'm extremely bullish and excited about. I think we're at the cusp of a major revolution in how storage systems are built because of these capabilities now. So for T09, you really don't want to allocate pretty much anything more than a few gigabytes of your most expensive tier, unless you're able to afford to go to 130 gigabytes or your SLA requires it. On the other hand, we have T15, and T15 gets all of its benefit in the first couple of gigabytes of the most expensive tier of memory, and you can give it as much as you want after. It's just going to flatline. And so imagine co-locating T09 and T15. We would be able to reason through a fairly simple logic and a very simple heuristic on how to allocate resources. Obviously, you want to give your initial set of resources to T15 and all the remainder to T09 until you get to about 130 gigabytes. At that point in time, perhaps you have a T20, and now you can start to allocate the next set of resources to the T20 workload, because that particular workload, interestingly, benefits from each additional megabyte of memory you give it. Understanding this notion of a fully autonomous adaptation takes a moment. So I wanted to start off by talking about it at a very abstract level. Imagine a hypercube. Now, in this particular case, we've just brought it down to 3 dimensions. And this hypercube is showing us a bunch of different parameters of the system. An example of this could be a read-ahead parameter. Another could be cache block size. Another is size-based partitions, like say in the memcache delec system. And usually most storage systems have several dozen of these parameters, each with a certain range of values. But to be able to fit it on a 2D plot here, I'm just showing a 3D model of this. Each dot represents the optimal policy for a single workload. And so each of those points then is the 3 tuple of parameters 1 settings and 2 and parameter 3 settings that result in that particular workload ending up with its optimal performance. Now, as you can see, workloads have dramatically different optimal policy points and parameters. And these today we set as a one-size-fits-all. And of course, it is not true that one-size-fits-all, but that's what we do. We do it in the lab, and we ship our systems based on sort of the least bad combination of our parameters based on performance experiments done by our brave performance engineers who are running these workloads, running benchmarks, and studying customer environments. When problem reports come in to try to guess at the optimal setting. A huge amount of opportunity and performance is left on the floor because of the wide variety of workloads and their characteristics for which we could actually, if we did it in the field in a fully autonomous system, adapt. So now with that abstract background, let's look at a very specific example. So this example, we have the same workload for which we are plotting these performance models. And what we're seeing is that depending upon different parameter settings, these are actual performance latency behaviors of the same workload just run with different parameter settings. And you can see how big the difference is. It's easily a reduction of 50% in latencies depending upon which parameters you pick. Now, the question is, how do you pick this? And of course, a different workload will have completely different shape. This is where a fully autonomous system that is able to do real-time modeling and become self-aware and do what-ifs on these in real time, given the latest technology that we have available to us, and then reason through and dynamically adjust these parameters to hug the lowest possible curve across all of these, right? And dynamically switch between parameters based on the conditions, both internal to the system as a self-awareness as well as in the environment from the workload. So in the top row, we're seeing a latency ratio against between the best and the worst case, the latency ratio of different allocations provided to different workloads for a given cache system in this case. The black lines are the envelope of the best and the worst possible performance that could be achieved. And the red line is dynamic adaptation of an algorithm that dynamically is figuring out what's going on. In the red line, a system that does not have any hints other than really trying to understand and become self-aware. And we're evaluating the performance results that we have seen around those, right? We've seen up to 69% of potential gain for Lears, which is a very powerful eviction system. And then plain LRU, we've seen 50% improvement. 50% of the potential gain was able to be captured by the dynamic adaptation systems. The lower row is a very similar type of experiment, but now changing algorithm-specific parameters and not just optimization parameters that we've added to the system as part of the knowledge gain that a fully autonomous system is able to utilize that other systems cannot. So the bottom row is more standard prosaic parameters that already exist in, for example, 2Q, layers, etc. And we're iterating over those parameters. Again, you can see that the dotted lines are the offline determined best and worst, lower is better, and dynamic adaptation system operating in real time at nanosecond level costs, tens of nanoseconds costs per IO, is able to achieve self-awareness and hug very close to the best possible performance in most cases. So here what's happening is that a fully autonomous system can achieve a very interesting set of optimizations which have to do with thrashing mitigation. And thrashing is something that's very hard to define at runtime, but if you're able to build these real-time performance models, you can detect it and take certain evasive maneuvers. And those evasive maneuvers basically take the purple point that is currently operating at about 45% miss ratio and actually drive it to the convex hull by doing a very clever curve steering that can only be done if real-time models are continually updated. So here, we're able to actually do curve bending. This is the very first time curve bending has ever been possible in real time, where we can take the actual customer workload that is hitting the storage device and understand its intrinsics so carefully that we can divide the workload into more than one class and do it completely dynamically and tweak those classes separately from each other. We're actually dynamically changing its conditions so that the accelerator gets a second layer boost, right? A second booster rocket, if you will. So as you can start to get the feel of fully autonomous systems actually being able to do things that simply just could not be done before, right? Again, these are things that are different from other domains like self-driving cars, where a really attentive driver can accomplish most of the things that a self-driving car can't. But in the world of storage systems, a really attentive operator simply cannot do certain class of things that a fully autonomous system can. And now we sit at the cusp, what I believe could not just be incremental improvements in efficiency and performance, but order of magnitude jumps in performance and cost improvements because of fully autonomous storage systems. So remarkably, we can use the same sort of technology in fully autonomous storage systems to achieve QoS targets. So for example, this red curve, which you've seen in one of the animations earlier in my deck, that it is actually a very dynamic curve. So I'm just taking a single snapshot of it and showing it here. But that dynamic curve, we can model that curve as a self-awareness mechanism inside the storage system and be able to understand exactly what the various dynamic autonomous tier allocations need to be for this workload to achieve any arbitrary performance target. So again, this is an industry first. It's never been done before to be able to take a 95th percentile, for example, or 99th percentile target that a user sets for a workload. In this case, I'm giving an example of 7 milliseconds, and have that be dynamically enforced by the autonomous storage device by varying the allocation tiers constantly to always fit just the right amount of the working set of the application to be able to hit those SLAs at arbitrary percentiles. So this is, again, something that could never be done without fully autonomous systems. And finally, multi-tier systems are the norm now, as we've already discussed. So how do you allocate across these tiers for a given workload to achieve the cost and QoS targets of that workload? And again, a fully autonomous system is able to do that multi-tier allocation. So hopefully this gives an idea of how I envision and how we're working together as an industry or across these various components, across the various areas of performance management, which can be done autonomously now with the latest tools available. Thank you very much. My contact information is irfan@magnition.io, and you can find me on Twitter at virtualirfan. Thank you so much for attending.
All right. Unfortunately, the video seemed a little fast, and I think there were some people who wanted to know a little bit more. If you have any questions, we have a few moments for a few questions. Let's just, I'm just going to take a look here. And I don't see any questions at the moment. Okay. Correct. I don't see any question at the moment, but thank you so much, Irfan, for spending time with us here at SODACON 2021. It has been my great pleasure to have you on board, and we hope to see you at future events. And I'm definitely looking at Magnition and looking at autonomous storage systems. I believe we are having some projects on the same lines. I feel some of our developers will definitely be getting in touch. Thank you so much for spending your valuable time with us.
Most welcome. Thank you.
Right. With that, now we will now move on to the next track, and that is the state of Kubernetes storage by Xing Yang. If you could all just join me in the next session.